I need to start with a small apology. The title of this video is a little bit clickbait. But you clicked on it, so hopefully it did its job and piqued your interest. Now, first disclosure. I use Claude all the time. Actually, all the time might be an understatement. On most days, by around 10:30 in the morning, I have already run out of tokens and I need to wait several hours before I can use it again. I love Claude. I think it's exceptional. It actually has completely changed how I research, write, analyze information, and also challenge my own idea. At this point, I almost find it difficult to imagine working without it. But there is one thing that drives me slightly crazy. Whenever I start using Claude in a scientific context, particularly biology or chemistry, I am often moved to a less capable model because the subject is considered too sensitive. I understand why safeguards exist around biology, I really do, but it creates a strange situation. Claude is apparently capable enough to transform how I work, but its most advanced capabilities are considered too sensitive to use freely in my own scientific field. So why should I trust it blindly? That is really what I want to explore in this video. I don't distrust Claude because I think it is useless, quite the opposite. I use it constantly because it is remarkably useful, but I distrust it in the way a scientist should distrust any powerful tool, including our own intuition, by the way. So I want to understand where it works, where it fails, and what evidence supports its output. I completely understand why many scientists remain skeptical about Claude and about AI more broadly. What I understand less is the double standard. As this is not something I have only observed online, I experienced it directly. A few years ago, I was responsible for a collaboration between a pharmaceutical team and an AI company. The process was quite straightforward. The AI company used its model to generate compounds that it predicted would be active against one of our targets. It will send us the list and we will review the compounds with our medicinal chemist, synthesize a selection and then test them. At least that was the idea. Because quite often when the list arrived, the response was, no, I don't like these compounds. My intuition tells me they won't work. The people who designed them clearly don't understand the biology or the chemistry. Sometimes those objections were completely justified. Experienced medicinal chemists can immediately identify problems with synthesis, stability, toxicity, or developability. That expertise is incredibly valuable. But sometimes the compounds were rejected simply because they didn't look like the compounds our chemists would have designed. Perhaps the chemists were right, perhaps the model was wrong. But if we refuse to run the experiment, we will never know. We were asking the technology to give us a different answer and then rejecting the answer because it didn't resemble the one we already knew. Over the past few years, I have seen this pattern repeatedly in discussion about AI, virtual cells, and computational drug discovery. A company publishes a result and the response is not simply the evidence is insufficient or this benchmark is weak. Very quickly it becomes these people are not biologists. They don't understand what they are doing. Anyone who has spent time in a laboratory will know this is pointless. Some of the criticism is perfectly valid. A binder is not a drug. Stronger binding does not automatically mean better efficacy. A virtual cell is not a complete representation of a living organism. Accelerating discovery does not automatically compress the entire journey to an approved medicine. We should challenge exaggerated claims. But correcting a claim is very different from deciding that people coming from another field have no place in biology. I have also noticed that we judge AI much more harshly than we judge ourselves. If a model makes one error, we often conclude that it cannot be trusted. But are we perfect? A well-known Nature survey found that more than 70% of researchers had, at some point, failed to reproduce another scientist's experiment. More than half had failed to reproduce their own. I can tell you that's the case in my own PhD. There are some experiments that were extremely difficult to reproduce. I have spoken with pharmaceutical teams that considered variation of up to 50% acceptable when certain experiments were repeated. Biological variability is not the same thing as an algorithm making a bad prediction, but it reminds us that science has never operated with perfect measurement or perfect human judgment. When a colleague gets some things wrong, we look at the assay, the protocol, the data and the context. We repeat the experiment. When a machine gets something wrong, we are sometimes tempted to dismiss the entire approach. The standard should not be perfection. It should be whether the technology performs better than the relevant alternative under realistic conditions. I think some of the discomfort comes from something more personal. Many life scientists are not coders. They have spent decades becoming experts in biology, chemistry, or medicine, and suddenly a new discipline has arrived in their field with its own vocabulary, methods, and forms of expertise. Not fully understanding something that may transform your field is very uncomfortable, particularly when the people introducing it sometimes speak as if everything you have learned can be replaced by a sufficiently large model. Because to be fair, technologists have their own form of arrogance. Silicon Valley has celebrated moving fast and breaking things. That becomes much less attractive when the thing you might break is a clinical trial or a patient. Biology is not a software. Regulation is not an annoying obstacle. And a failed experiment cannot always be corrected with the next product release. This is therefore not only a disagreement about evidence, it is a clash between two cultures. You can see it in the reaction of Anthropic recent work on protein binders. Anthropic reported that Claude generated experimentally confirmed binder against 14 of 15 targets. That is interesting. It does not mean Claude discovered 14 drugs. It tells us nothing yet about efficacy in a disease model, toxicity, developability, or clinical benefit. But dismissing the result because binding is not drug discovery also misses the point. The team included scientists with pharmaceutical experience. The proteins were synthesized and tested externally, and the experimental data were released. It is not a drug, but it is not nothing either. We also need to be honest about the performance of our traditional model. More than 90% of candidates entering clinical development still fail. Development costs continue to rise. The FDA approves roughly 50 novel medicines in a typical year, with thousands of rare diseases still have no authorized treatment. Approved drugs act on fewer than 900 human proteins, while several thousand proteins are considered potentially druggable. Continuing to do everything as we have always done is not a serious answer. The way forward is probably in that messy gray zone between the two extremes. Technology is not the be-all and end-all of scientific discovery, but traditional scientific practice is not the only legitimate way forward either. We need technologists who respect biology, experimental evidence, regulation, and the responsibilities that come with developing medicines. And we need life scientists who are willing to test unfamiliar ideas, even when those ideas come from people who did not follow the same curriculum or spend the same years at the bench. In my compound example, the solution was never to trust AI blindly. It was to agree on objective criteria, test compounds proposed by both the model and the chemist, and let the experiment tell us where each approach succeeded and failed. We should not trust a molecule because an algorithm generated it, but neither should we reject it simply because it looks unfamiliar to an experienced chemist. Science needs skepticism, it doesn't need gatekeeping. And ultimately, neither human intuition nor AI companies' press release should have the final word. The experiment should.